સ્વાગત કરીએ છીએ પ્રોફેસર વિરજ છે એ હંમેશા એમના ભાવના રહી છે. મેં હમણાં જ કહ્યું કે પ્રસાદભાઈ અને વિરેશભાઈએ પેલી જે ટેસ્ટ છે ટફ ટેસ્ટ ટીચર્સ માટેની સ્વેચ્છાએ પાસ કરી છે. પ્રગામી તરંગમાં લખતા રહે છે, ગુજરાતીમાં પણ લખે છે અને અંગ્રેજીમાં પણ લખે છે અને જુદી જુદી સ્પર્ધાઓમાં પણ ભાગ લીધેલો છે. નેશનલ એસે કોમ્પિટિશન એ મને યાદ આવી ગયું.
Coordinator of CPEX.
And now, yeah, CPEX એટલે કોમ્પિટિશન ફોર ફિઝિક્સ એક્સપેરિમેન્ટ્સ એની જવાબદારી સંભાળે છે. અને આજે એમણે જે ટોપિક લીધો એ પણ જે વાત ચાલતી હતી એમાંથી અથવા તો આ ટોપિકમાંથી એક વિશેષતા રૂપે 1927 બોર આઇન્સ્ટાઇન ડિબેટ અને ત્યારથી પછી જે વાત ચાલી તે તો હિસ્ટોરિકલ ડેવલપમેન્ટ્સ કેમ આપણે IYQ 2025 એવું ઉજવીએ છીએ. તમે યુનોનું રિઝોલ્યુશન જોજો કે છેલ્લા 100 વર્ષમાં જે પ્રગતિ થઈ પ્રશ્નો ઉદ્ભવ્યા, ચર્ચાઓ થઈ અને ચર્ચાઓ તો એક બાજુ ચાલતી હોય, પેલા લોકો ટેકનોલોજી ડેવલપ કરતા થઈ ગયા. એ બધી વાતોની શરૂઆત થઈ હતી લગભગ 100 વર્ષ પહેલા. એની જ કંઈક વાત કરવાના હશે હું એમ સમજુ છું. અને એક કદમ પર એક ડગલે જે સનસનાટી ફેલાઈ ગઈ. 1924 બોઝ અને ડી બ્રોગલીની વાત થઈ. 25 માં શું થયું, 26 માં શું થયું, 27, 28 જેની વાત આપણે આમ તો કરી નોબેલ પ્રાઇઝ ફોર રામન. એ બધી રસપ્રદ વાત કહેવા માટે આજે આપણી સમક્ષ ઉપસ્થિત છે પ્રોફેસર વિરેશભાઈ ઠક્કર.
Mechanics. I know that my job is tough in two ways. I am following an excellent presentation by Prutulbhai. So the tempo is set and I have to maintain that. That is a big challenge for me. And second, the most important is that I am standing between you and your lunch. So that is another aspect I have to keep in mind while delivering this talk. So I hope you will enjoy this. Only point I will like to comment in the beginning is that so it is just going to be an historical survey of quantum mechanics and its development. So let me begin with my outline, what I am going to talk in this presentation. So start with introduction, then I will talk about James Clerk Maxwell, Henry Hertz, black body radiation, Max Planck, other developments, photoelectric effect, Arthur Holly Compton, Louis de Broglie, Davidson Germer and J.B. Thomson, Erwin Schrödinger and Max Born, P.M. Dirac, Werner Heisenberg, something more, and I will conclude. Don't worry for the long list of the outline, it will not last more than 1 hour. So I will not make you wait for lunch too long. Okay, so let me begin with the introduction. And before I introduce this quantum mechanical development, this is my habit of giving some quotes. My students are here and they know, they are smiling. So I always start with some quotes, and fortunately or unfortunately, 2 of them were already there in the presentation by Pratul sir. So they may be repeated. But anyway, I didn't edit it, it is still there. So the first one, very interesting. The history of physics, there have been 3 great revolutions in thought that first seemed absurd yet proved to be true. They proposed that the earth, instead of being stationary, was moving around at a great and variable speed in the universe that is much bigger than it appears. Second one is the theory of relativity, and the third one is that of quantum mechanics, जिसकी हम बात करने वाले हैं. And it was said by Edward Taylor. I like relativity and quantum theories because I don't understand it. Same is the case with me also, so don't worry. Okay. Then those who are not shocked, you saw that by Niels Bohr in Pruthul sir's presentation. Nobody understands quantum mechanics. One famous quote. You will listen to this throughout the years whenever you go to such kind of presentations or talks. The only thing that quantum theory has going for it is, in fact, it is unquestionably correct, and that is by Michio Kaku, the greatest of the physicists of recent times, Michio Kaku. Okay, fine. So let me begin with the introduction, and I start with one of my favorite statements of physics. Okay, whenever we start discussing physics, we say that physics is a study of nature and everything. So then after that, I start with the statement that whatever is there in our surrounding can be classified into two categories, either matter or radiation. Whenever we think of matter, the next statement, the next thought that comes to our mind is that matter is made up of large number of particles. Okay, and on the other hand, when we think of radiation, then we think that radiation travels as a wave. Okay, whatever is there in surrounding, this stage, myself, yourself, the chairs, the walls, everything is matter. And this matter is made up of large number of particles. The concept of particle is there in our mind. Radiation, the light coming from this different sources present here or the projector, that travels in the form of a wave. Wave and particle, they are two different aspects and they have different properties also. We know it very well. So there is known to everybody, and particle and wave are treated separately, and the different principles are applied to them for their analysis. All of us know that. Experiments related to the wave and those related to the particles are also different. All of us are physicists and physics students, and we do experiments in the laboratories, and we frequently deal with particle aspect and wave aspect, and we have different experiments for these two aspects. Electron is reckoned as a particle because it has particle properties. When we use the word particle, some properties of particles come to our mind, like mass, charge, momentum, and so on. On the other hand, the electromagnetic radiation is considered as a wave because it has wave properties such as amplitude, frequency, wavelength. Superposition principle is applied to waves and so on. Okay? They experience the wave phenomena such as interference, diffraction. However, it was realized that electrons and electromagnetic radiation may possess properties different from what we have noted just now, and that is because of quantum mechanics. And that is what we are supposed to discuss today. Okay. So I once again take you back to 17th century. In my classes I discuss some history of physics, whatever little bit history I know before coming to the actual point. So here also just I will take, before we come to quantum mechanics and its real development, we start our journey from the 17th century, where two great scientists, Isaac Newton and Christian Huygens, they had proposed two different theories on light. They had two different ideas about the propagation of light. One proposed by Newton is called the corpuscular theory of light, in which Newton considered that light travels in the form of particles which he called corpuscles. So that's why it is called corpuscular theory of light. With the help of that theory, it was possible to explain reflection, somewhat of refraction, and rectilinear propagation of light. And because he had got fame because of his laws of motion and the law of universal gravitation, his theory was readily accepted, that light travels in the form of particles called corpuscles. And that's why when Huygens proposed this theory in 1676 about the wave nature of light, nobody accepted that theory and nobody could believe in that wave nature of light. Unfortunately, Huygens died in 1696, and by that time nobody believed in his theory. Finally, more than 100 years later, Thomas Young performed this experiment of double slit. You know that Thomas Young and double slit experiment, which produced the interference pattern, and to explain interference pattern it was required to use Huygens wave theory. So more than 100 years after his death, Huygens theory became acceptable after this historical experiment, and this is according to me one of the best top 10 experiments ever performed in the field of physics. Joshipura sir distributes one of the nice books on physics, top 10 most beautiful experiments of physics written by Ajoy Ghatak sir. But my list is slightly different, and I call them top 10 best experiments according to my opinion, and this is one of them, the Young's double slit experiment, which required the use of Huygens wave theory to explain why the fringes are observed. And in that curtain laser program of this IYQ hosted by IAPT RC7, very first lecture presented by Ajoy Katak sir, and he had said one nice statement. In this experiment, what was observed, light plus light produces darkness.
That was the statement by Dennis Gabor.
Dennis Gabor, I forgot the name. Dennis Gabor, who is responsible for laser and TIR, total internal reflection. Okay, fine. So, thank you, sir. Then I come to James Clerk Maxwell. As I mentioned, Huygens said that light travels as a wave. But what is the nature of that wave? What properties of this wave possess? That was not actually mentioned by Huygens. The nature of light or wave as in the form of light. It was proposed by James Clerk Maxwell in his theory in 1864. In this theory, suggested that an accelerating charged particle, such as an electron, generates linked electric and magnetic disturbances. This is the principle of that experiment performed by Hertz. If the charges oscillate periodically, the disturbances are waves whose electric and magnetic components are perpendicular to each other and to the direction of propagation, like this. So all of us know this electromagnetic wave character of light. We know this. He wished that during his existence somebody could succeed in generating electromagnetic waves in the laboratory. The theory was proposed in 1864. Unfortunately, he died in 1879, 15 years after the publication of his theory. And by that time, nobody was able to prove that electromagnetic waves can be generated in the laboratory. 8 years after his death, Heinrich Hertz performed that experiment and produced the electromagnetic waves in the laboratory for the first time. Okay, and this is the historical setup of Hertz experiment, in which he was able to produce the electromagnetic waves. This is the spark gap. These are the two spheres. The rods are connected to induction coil, and this is the receiving spark gap, which will receive the generated electromagnetic waves. So this is the historical setup of that experiment. But it happened after the death of Maxwell. Hertz was able to produce the waves. So it was confirmed that the electromagnetic radiation has a wave character, and Maxwell's theory is right. Not only that, Maxwell has said that light is a kind of electromagnetic wave from the measurement of the speed of the electromagnetic wave and the speed of light experimental value. But here comes a twist in the story. In the same experiment performed by Hertz, he made UV rays incident on one of the two spheres I showed you in the previous figure. And what he found, the spark, intensity of spark increases there in the spark gap. He noticed that, but he did not give much thought over that idea. Okay, why did it happen? Why was that intensity of spark increased? Okay, so you might have got the clue for what I am talking about. When UV light was made incident on one of the spheres, there was one phenomenon occurred, and that phenomenon is nothing but photoelectric effect. Because of photoelectric effect, more number of electrons were emitted that increased the intensity of spark. That was noticed. Now, the fact is that the phenomenon of photoelectric effect cannot be explained using Maxwell's electromagnetic wave theory. The experiment which confirmed that what Maxwell said is correct, that electromagnetic waves are existing, they can be produced in a laboratory. In the same experiment, one more phenomenon is observed, which proves that this is not the whole story. Okay, so the detailed study of photoelectric effect was done by Leonard in 1902. But before we go to, I am just going in a chronological order. Okay. So before we go to 1902, Leonard's experiment, let me discuss one more phenomenon which also laid foundation stone of quantum mechanics. Okay, that is nothing but black body radiation. Scientists called Gustav Kirchhoff performed the experiments on black body radiation. Sometimes it is also called cavity radiation. And he had these experimental results. Everybody knows these results. that the relative intensity of emitted radiation versus wavelength graph for different temperatures. And this is experimental result. And physics is a science in which there is an equal importance of theory and experiment. So if somebody suggests one theory, that has to be experimentally tested before it becomes acceptable. Or if some experimental results are there, there has to be some theory which could explain those experimental results. Okay, so this is the experimental result, this graph, and it requires some theoretical explanation. Okay, so the first try made was that this graph is experimental, which needs, I told you, that theoretical explanation. The first person who tried to explain this was Wilhelm Wien, who used the laws of thermodynamics to explain this graph, and he arrived at this equation we know. Lambda m into t is some constant b, which is called Wien's constant, and this equation is also called Wien's displacement law. Using this theory of Wien, it was possible to explain only the lower part of this graph, lower wavelength region rather, of this graph, not the entire graph. So Wien's theory, using the principles of thermodynamics, could not explain this graph completely. So the next attempt was made by two scientists, Lord Rayleigh and James Jeans. They used Maxwell's electromagnetic wave theory to explain this graph, and they got this equation of energy density. What happened is that using this equation, it was possible to explain this part of the graph, means higher wavelength region of the graph, but not the entire graph, the same story. Using Wien's equation, it was possible to explain this part of the graph, and using Rayleigh-Jeans equation, it was possible to explain this part of the graph. But there was one flaw in the theory of Rayleigh-Jeans, that it led to the phenomenon called ultraviolet catastrophe. That as you just notice the wavelength change, but smaller wavelengths, as per this equation, the graph goes up. So for large frequencies, the energy density goes to infinite, which is from the law of conservation of energy not possible. And that flaw is ultraviolet catastrophe. So none of the theories we discussed, Wien's theory or Rayleigh-Jeans theory, could explain this graph completely. Finally, we come to Max Planck, who in 1900 was able to explain that. But before we go to his theory, just interesting fact, Wien's colleague Max Planck was quite aware of the problem of this black body radiation and failure of the then existing theories. One was based on thermodynamics, the other one was based on Maxwell's equations, Maxwell's electromagnetic wave theory. So the then existing theories could not explain those experimental results, or in other words, to explain the graph of the black body radiation completely. It was not possible. So this graph, as I told you, was not explained completely. Planck suggested one hypothesis, and based on this hypothesis, he derived this equation. For the energy density per unit wavelength, with the help of which it was possible to explain the complete graph of the black body radiation. So it took him almost 6 years to get to this result, but he was quite skeptical about presenting his idea to the scientific world. So he was ready with his explanation, but he was not ready to publish it. But because during that time, during that period, the radiation was considered to be emitted in the form of a wave, as per that Maxwell's electromagnetic wave theory, in a continuous fashion, due to the successful Maxwell's theory, and it was something like this. But Planck had a different idea. He said that the walls of the cavity emitting radiation are made of tiny dipoles, which continuously oscillate with definite frequency, called their characteristic frequency, and during their oscillatory motion, they emit electromagnetic waves of the frequency with which they are oscillating. Okay, so the radiation is not emitted in a continuous manner, but as it was thought classically. Further, he said that the energy of the emitted radiation depends on the frequency as contrary to amplitude. As per electromagnetic wave theory by Maxwell, energy of the wave depends on square of the amplitude we know. But Maxwell had a different idea. He said that energy is not a function of amplitude, it's a function of frequency. So we know this equation, famous equation, E is equal to nh nu, where n is an integer, takes values 1, 2, 3, etc. And this equation leads to quantization of energy of the radiation. because the first possible value of energy will be h nu, corresponding to n equal to 1. The next value will be 2h nu, corresponding to n equal to 2. No other value between h nu and 2h nu is allowed. 1.1 h nu not there, root 2 h nu not there. So there is quantization of energy. In other words, the radiation is emitted in the form of discrete packets of energy like this, h nu followed by 2h nu, then 3h nu and so on. Each packet of energy he called a quantum of energy. The quantum of energy was named photon in 1926. So as per Max Planck, the radiation is emitted in the form of photons. And as I told you, he was skeptical about its publication. Finally, on the suggestion of one of his friends, one of his friends was able to convince him to publish this theory. And 14th of December 1900, this theory was published in front of German Academy of Sciences. And as expected, nobody accepted that theory warmly or willingly at that time. But before we discuss detail about that, some other developments, very interesting developments. I have taken you from 1860s to 1900, okay? But in between, the period of 5 years from 1895 to 1900 is very important from the history point of view of physics. So during these 5 years, at least one thing has happened every year, 1895 to 1900. So let me talk about that. Okay. So in the last decade of that 19th century, many people were working on discharge tubes and experiments related to discharge tubes. One of them was Wilhelm Röntgen. During one of these experiments, he accidentally discovered X-rays in 1895. Okay, and he was awarded the first Nobel Prize of Physics 1901 for this discovery of X-rays. Then followed by in 1896 another important event. The Dutch man Peter Zeeman observed the splitting of spectral lines in the presence of magnetic field. Magneto-optical phenomenon all of us know. Okay, this phenomenon is called Zeeman effect, for which he was awarded Nobel Prize in the next year, 1902. The same year, 1896, a Frenchman, Henri Becquerel, working on X-rays, accidentally discovered natural radioactivity, 1896, and for which he was awarded Nobel Prize in the following year, 1903. So this is Henri Becquerel, and this is the radioactivity, we know that phenomenon. Then following year, 1897, J.J. Thomson discovered electron, okay, in this experiment called cathode ray tube. 1897, the first particle to be discovered within the atom. Still in 1897 rather, atom word comes from the Greek word atomos. Atomos means uncuttable, indestructible. So till 1897, atom was an atom, uncuttable, indestructible. This was for the first time it was possible to look inside the atom and found something from the atom, something emitted from within the atom. It was of course called cathode rays initially, later on it was electron. So in 1898, Madame Curie and Pierre Curie succeeded in separating two elements, radium and polonium, from an ore of uranium called pitchblende. They found these two elements were much more radioactive than uranium. Baap numbari, beta 10 numbari, like that. The elements obtained are much more radioactive than this. They shared the 1903 Nobel Prize in Physics along with Henri Becquerel. So now, of course, 1899 I did not mention. 1899 actually Rutherford was able to identify two radiations, alpha and beta. He was able to find out that the radioactive radiations are of two types, positively charged and negatively charged. Alpha, beta, he named them. In 1900 we saw that publication of Planck's theory. So now we come to photoelectric effect. So as I mentioned, John Lennard performed this experiment of photoelectric effect in detail. Okay, the experimental arrangement, the experimental results are there. This is the experimental arrangement, the photosensitive surface anode connected to an emitter and a battery and for different potential differences, current is measured as a function of intensity of light and frequency of incident light, and this graph was obtained. And this, once again, these are the experimental results of photoelectric effect which require theoretical explanation. So once again it was tried to explain this graph with the help of Maxwell's electromagnetic wave theory, but it was not possible to explain this graph using Maxwell's theory. Finally, in 1905, a 26-year-old clerk of class 3 working in a patent office of Switzerland came up with a theory to explain them. And I hope you have got the person whom I am talking about, nobody else but the great man Albert Einstein. When he published this explanation, he was not a scientist, neither a professor nor a teacher. He was working as a class 3 worker in a patent office of Switzerland. And then 1905 is of course the miracular year in the history of physics, in which he published not one or two research papers, 5 different research papers in 5 different fields. He accepted Planck's hypothesis with one modification. Planck had thought that radiation is emitted and absorbed in the form of discrete packets called photons. We saw that. But as per Max Planck, propagation of the radiation takes place in the form of a wave. Einstein modified it by saying that even the propagation also takes place in the form of discrete packets. And with this modification, he got these 2 equations, and with the help of these 2 equations, he was able to explain all the experimental results of photoelectric effect. And we know that Einstein was given Nobel Prize for this explanation of photoelectric effect, not for E is equal to mc square. So the 2 phenomena, black body radiation and photoelectric effect, proved that radiation, initially they fabricated what is known as a mason, 1954. Later on it was extended to laser by Theodor Maiman, the first ruby laser. It is there in the hand of Theodor Maiman, 1960. And these 2 devices, laser and maser, they are based on Einstein's theory of stimulated emission. So now we come to Arthur Holly Compton. 1923, American physicist Arthur Holly Compton demonstrated the experiment in which he was able to demonstrate the particle nature of radiation in the form of photon. He showed that the collision between an electron and a photon takes place just like a collision between 2 material particles. So that confirmed that the photon has particle properties. Okay. The phenomenon is called Compton effect, and it is also considered to be one of the milestones in the development of quantum mechanics. 3 phenomena are the milestones in the development of quantum mechanics. One is black body radiation, I discussed that. Second one is photoelectric effect, and third one is this Compton effect. He was awarded Nobel Prize in 1927 for Compton effect. Now we come to the last part of this my presentation. There is Louis de Broglie. Historically we have started from 17th century, and chronologically we have gone through different developments in the ideas of wave, particle and everything, matter and radiation. Now we come to Louis de Broglie, Frenchman. Doing his PhD, he wrote a sentence in his PhD thesis which his supervisor Paul Langevin found to be misfit. But on the second thought, his guide allowed him to keep the sentence in it. We know this. He came up with a hypothesis which was partly based on intuition and partly based on symmetry observed in nature. See, in the beginning, I started with one statement which I told you, my favorite statement with which I start my talks on physics. That whatever is there in our surrounding is classified into 2, either matter or radiation. From the experiments we saw, it was confirmed that radiation has dual character. Sometimes it behaves as a wave, sometimes it behaves like a particle. Now if nature believes in symmetry, so should be the case with matter also. Matter should not always behave like a particle, it should also have some wave nature. Okay. So not only he gave this hypothesis, but he also obtained the equation for the wavelength of wave nature of the particle. We all know that it is lambda is equal to h by p, but this is one of the most significant equations of physics according to me once again. Because on the left hand side, if you look at the quantity, it is lambda, which is wavelength. And wavelength is a property associated with a wave. On the right hand side, we have a property momentum P, and momentum is a property of a particle. So on one side of this equation, you have a property associated with a wave. On the other side of the equation, you have a property associated with a particle, and they are related by a universal constant h. Lambda is equal to h by p. So one of the greatest equations of physics. The dual nature of radiation was already proved, but that of matter was suggested by de Broglie and was yet to be proved. So dual nature of radiation was already there. As I told you, the phenomena like interference, diffraction, polarization, it requires Huygens wave theory. Light travels as a wave. The phenomena such as black body radiation, photoelectric effect or Compton effect requires particle nature. So it was confirmed that radiation has dual nature. But the matter, dual nature for matter was yet to be proved. Fortunately, within no time, within 4 years, 2 different experiments were performed which confirmed what de Broglie said is correct. One set of experiments was performed by Davison and Germer, the other one is by J.P. Thomson, and both these experiments proved that electrons are diffracted and diffraction of electron requires wave theory. So it was confirmed that electron behaves like a wave in these experiments. So Davison and Thomson were awarded Nobel Prize in Physics for their work. I don't know why Germer was omitted from this Nobel Prize. The interesting thing about this Thomson, J.P. Thomson, I mentioned J.J. Thomson previously in my presentation. Okay, so J.J. Thomson was given Nobel Prize, as I told you, for the discovery of electron. Not only that, he measured properties of electrons in that experiment, and he said that electron has particle properties. J.P. Thomson is a son of J.J. Thomson. The father says electron has particle properties. The son says electron has wave properties, and both have win Nobel Prizes. એટલે બાપ દીકરાને બનતું નથી હોય જવામાં બી હતું. અત્યારે છે એવું નથી.
તો ઇનામ મળતું.
તો એને નોબેલ પ્રાઇઝ મળતા હતા સાહેબ. ઇનામ એટલે નોબેલ પ્રાઇઝ, ટોપ મોસ્ટ.
કોમ્પ્લિમેન્ટરી था.
અને એની સામે એક બાપ દીકરાની પેર એવી છે કે સેમ ફિલ્ડમાં સેમ કામ કર્યું અને they won Nobel Prize. W.H. Bragg, William Henry Bragg, William Lawrence Bragg. They work on the same field and they were jointly awarded Nobel Prize for, you know, Bragg's equation, Bragg's law, n m equal to 2d sin theta. And of course, Lawrence Bragg holds the youngest Nobel Prize winning age. Okay, till now.
Viresh, you can say Thomson and Thomson as an example of generation gap.
Yeah.
One saying particle, another saying wave.
And both of them are correct. Both of them are correct.
And who said that? Louis de Broglie. Both of them are correct.
There is third pair of father and son who won the Nobel Prize. Just baat nikli hai to. Bohr, we not talked about that. Niels Bohr. He won Nobel Prize for his atomic model, so atomic theory. His son, A.G. Bohr, won Nobel Prize for nuclear physics. Okay, so 3 father and son pairs are there who won Nobel Prizes, as far as I know. But this is a unique case. Okay, J.P. Thomson and J.J. Thomson. Okay, so this is the experiment by Davison Germer, and this is that by J.P. Thomson. All of us know that. So now we come to Erwin Schrödinger and Max Born. Meanwhile, an Austrian physicist, Erwin Schrödinger, obtained an equation now called wave equation 1925. It involves what is known as a wave function, which completely describes the particle. Very important word. Completely describes the particle. Once you know the wave function, particle is completely disclosed. You know everything about the particle. Okay. So if we know this wave function, we know everything about the particle. As a result, the whole new branch of physics called wave mechanics was developed, which is now based on Schrödinger's equation. The wave function we mentioned, but what is the use of wave function? How to use it for getting some information about the particle? That interpretation was given by Max Born in 1926, that modulus chi square gives probability density. All of us know that. So now we come to Paul Dirac. He was an English theoretical physicist who made fundamental contribution to the early development of both quantum mechanics and quantum electrodynamics. He also made significant contributions to the reconciliation of general theory of relativity with quantum mechanics 1926. Among other discoveries, he formulated Dirac equation. All of the MSc students use this equation in the advanced quantum mechanics. Described the behavior of fermions and predicted the existence of antimatter. He was the first person to talk about that something like anti-electron, we call it positron, should be existing. And within no time, within 4 years, it was discovered by Carl and Darshan. Okay. He is also credited with Fermi-Dirac statistics, and that applies to the particle having spin either half or odd multiple of half. These particles obey Pauli's exclusion principle also. Dirac shared 1933 Nobel Prize in Physics with Erwin Schrödinger. Now we come to Werner Heisenberg. He was a German physicist, contributed in the development of matrix formulation in quantum mechanics. So there are two different formulations in quantum mechanics. One is based on Schrödinger's wave equation, and the other one is based on this Heisenberg's equation, matrix mechanics. He is better known for his uncertainty principle, published in 1927. The uncertainty principle essentially puts a limit to the precision with which, uncertainty principle doesn't mean that the measurements are made with some false methods or there is some error in our measuring instruments, nothing like that. It is one of the fundamental principles of physics which is applicable in any case. Whether you use any other instrument, you will come across this, and it has to be accepted, it will be there. It has to be. So one of the fundamental principles of physics, that certain pairs of physical quantities of a particle can be measured. इसके लिए limitation है. Heisenberg was awarded the Nobel Prize in Physics for 1932. So this year 2025 is significant in the sense that two important events occurred exactly 100 years back. 1925, Schrödinger presented his wave equation exactly 100 years ago, and this formulation of matrix mechanics by Heisenberg. So we are commemorating this 100 years of these two great discoveries of quantum physics or quantum mechanics. Okay, so something more. 1932, British physicist James Chadwick discovered neutron, a neutral particle residing within the nucleus, for which he was awarded Nobel Prize. Once again, there is an interesting case here. As I mentioned previously, that electron was discovered by J.J. Thomson 1897. Proton was discovered by Rutherford 1919, and neutron discovered by James Chadwick 1932. Now the interesting thing is that Rutherford was a student of Thomson and Chadwick was a student of Rutherford. So Guru Chela, and all of them are contributors to the discovery of three most fundamental particles we know of the atom: electron, proton and neutron. Of course, Rutherford was not awarded Nobel Prize for the discovery of proton, neither for his atomic model he proposed in 1911, I mentioned you. Unfortunately, Rutherford was given Nobel Prize in chemistry, not even physics. Okay, and which he didn't like. So in his Nobel speech, he had one comment. He was very bold to say that, see, there is one famous quote by Rutherford. He says that all science is physics, the rest is stamp collection. So chemistry and biology, according to Rutherford, they are just hobbies, stamp collection. They are not sciences, only science is physics. Now, if a person who thinks that only one science is there, that is physics, if a chemistry people will award a Nobel Prize to him, what will be his reaction? And he was awarded Nobel Prize for what? Artificial nuclear transmutation. Artificial nuclear transmutation. So in his Nobel speech he says that the biggest transmutation I have observed in my life is my own transmutation from a physicist to a chemist. He didn't like it. So from this stage, he said this in Nobel winning lecture. Fine. So that was something interesting. After the works of Schrödinger, Dirac, Born, Heisenberg and others, the development in the field of quantum mechanics geared up and many more results were published. But I will like to stop here. So in the end, this is not the whole story as I told you. I might have missed some of the important events, but I have tried to cover whatever I know, I remember, and little bit I understand in this field. So, acknowledgement, Google Images, I have taken the photographs from that IAPT RC7 for giving me this opportunity to express my views from this platform. And of course, HNGU Patan, who has hosted this whole event and allowed me to speak from this stage. Thank you.
એ કાળો પદાર્થ નથી, એની વિશેષ એની વ્યાખ્યા છે અને કાળા પદાર્થને એક નમૂનો એપ્રોક્સિમેટ બ્લેક બોડી ગણીએ તો જૂના જમાનામાં જે આપણે ટંગસ્ટન ફિલામેન્ટનો બલ્બ આવતો હતો એ કાળા પદાર્થ તરીકે કામ કરે છે. અને દર્શનભાઈ આપણે જો અનુકૂળ હોય તો ફરી પાછા મળીએ ત્યારે 2 કે 3 મિનિટનો વિડીયો બતાવીએ કે જેમાં બ્લેક બોડી રેડિયેશનની કેરેક્ટરિસ્ટિક્સ બતાવવામાં આવી છે. ધ વિડીયો ઇઝ પ્રિપેર્ડ બાય IAPT RC7. Thank you so much. હવે આપ પ્રશ્ન પૂછો. You have asked a question because you asked last time.
Free, you are free to ask question either in Gujarati, Hindi or English. No problem at all. Just ask the question. If you do have any question.
See, Kalam sir had said once that no question is a silly question.
Yeah.
No question is a silly question. So, if you have any question, you are definitely welcome. Of course, I did not take anything much technically. Just as I told you in the beginning, I will just give a historical survey. Not much of a technical things were there, but this history also we should know. Fine.
Yes, sir.
Yes, sir.
One thing which I read somewhere, that Max Born was willing to come in India. That C.V. Raman has convinced him.
Yes.
Do you have any idea about that more than?
No, sir. No idea.
એ રામન પાસે આવવાના હતા એ એક સ્ટોરી છે ને પછી કઈ આગળ વાત
આગળ આયા નહીં અને એનું કારણ બ્રિટિશર્સ હતા.
Maybe.
એવું
I
કઈ
don't
નહોતું
know.
હતું.
Yeah.
If anybody knows anything about the answer, so they can.
Yes, Devans.
Yeah.
What do we mean by make uncertainty certain?
So it's challenge for the next generation. It's for you.
Certainly uncertain is there.
The answer is certainly uncertain.
Certainly uncertain exists.
So a Nobel Prize is waiting for you. If you can do that. Deliberately it was set there in the background. But you noticed it. Fine. So as I kept the promise, it is around 1 o'clock.
Yeah, one comment.
Yes, sir. Please.
Very important.
Please.
It is very important that it is not mentioned anywhere in the whole course of development in quantum mechanics. Wolfgang Pauli's contribution is seemed to be missing, and that is also very important. The Pauli's exclusion principle, 1925. So that's also 100 years of Pauli's exclusion, and it also has contributed a lot of development, including semiconductor chips and Fermi energy, Fermi surface, all the quantum first revolution that we are enjoying, and he has got very good
Spin
contribution.
statistics there.
Yeah.
It is there. I just mentioned it. I have mentioned it. The
don't
Pauli's exclusion principle. It was there one sentence, but actually I did not elaborate.
કારણ કે ઘણું બધું છે.
Yes, sir.
ઘણું બધું કહેવાનું
Yeah.
છે.
So I actually stopped at 1925. The rest of the things.
I'm also falling on
Yeah.
1925.
Yeah, but I have mentioned it. It is there in one of the slides. Okay.
Okay. If anyone has any question, you can ask. Otherwise, we will move forward for the lunch.
Yes.
Okay. So I am inviting you all for the lunch now.